तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. In a series of lectures on basic electronics, learning by doing, let us move on to the next one. Before we do that, let us recapitulate what we discussed in the previous lecture. You might recall in the previous lecture we discussed about transistorized differential amplifier. We discussed the basic differential amplifier formed by two transistors, what is known generally as the long tailed pair, and then we discussed about the different configurations like single ended, double ended input and output. We also discussed the AC and the DC configuration of the circuits and how a constant current source, when used for biasing the emitter of the two transistors, you can improve on the common mode rejection ratio. I hope you remember these things. Now we will move on to the next topic, which is integrated circuit operational amplifiers. All the discussions that we had so far is basically to prepare us to understand this idea of on the circuit and the applications of operational amplifiers. So before we go further, it is important to understand what is an integrated circuit, what are operational amplifiers, and what are its characteristics and what are its applications, which is most important for us for learning and applying electronics and different situations. So what is an integrated circuit? A preliminary background for understanding what is an integrated circuit was already given in the last portion of the previous lecture. Immediately after differential amplifier, I was mentioning to you that when you have the resistors, capacitors, all can be prepared along with the transistors on the same silicon chip, then you find they can be positioned very close to each other on the silicon chip, on the same silicon chip, and that means you can now have a whole circuit which involves basically resistors, capacitors and transistors together, all integrated, all the functionalities are integrated onto the same area of the silicon, and then it becomes a integrated circuit. It is no more a device like a transistor or a resistor or a field effect transistor. Now it is a whole circuit which has been now formed on the silicon chip. That is why it is called integrated circuit. It is all integrated on a very small region of the silicon chip by using what is known as a planar technology. In a planar technology, on the same side of the plane you are able to generate the various resistors, capacitors and transistors. We will see how it is in a moment. Before we do that, you can actually classify the integrated circuits into a number of ways. For example, there are monolithic circuits. Monolithic means one single silicon chip on which the entire circuit is built, then it becomes monolithic. You also have hybrid circuits where you will have some integrated components apart from some discrete components together forming a circuit. For example, making inductances is very difficult in integrated circuit, that I mentioned also earlier. Therefore, if I want to make a LC oscillator, I can actually integrate all the rest of the components onto the same silicon chip, and then also have the inductance alone put as a separate unit, discrete unit, along with this silicon chip, then form together, they together form whatever oscillator that you wanted to design. Then it becomes a hybrid, in the sense that there are two different types. You have an integrated version of the circuit, you also have a discrete version of the circuit, therefore we call it as an hybrid circuit. Together this entire thing can come inside a small package, and therefore it will still appear very small as an integrated circuit, but we know that it has got two different components. One is an integrated component, the other is the discrete component, both together incorporated into the same encapsulation. So that becomes the hybrid circuit, that becomes a hybrid circuit. Then if you take the monolithic circuit, which is the most popular among the integrated circuits, you would find you can have a monolithic circuits based on bipolar transistors, like normal BJTs, or what they are known as bipolar junction transistors, which are the usual transistors that we have been discussing about all along. You can also have another type of circuits built with unipolar devices. Basically unipolar devices are field effect transistors. Even among the bipolar, you can have in the design, actual design of the integrated circuit, there could be a difference. For example, there could be a p-n junction isolation or dielectric isolation. Let me not go deeper into that. Similarly, in the unipolar, you can have two different things: MOSFET, metal oxide semiconductor field effect transistors, or you can have junction field effect transistors integrated into the circuits. So the MOSFET, is the most popular among these two, and for several reasons. So you have different classification of the integrated circuits, and then you also have another type of classification in terms of the number of components that are integrated into the same silicon chip. Here the first picture I have showed is called SSI chip, which is the small scale integrated circuit. This chip has got different components in a smaller number, usually less than around 10. If you have on single silicon chip, then it is called SSI chip, small scale integration. But the dimensions, typical dimensions of such a chip will be, for example, 1 mm by 1 mm square with a very small width or thickness about 0.4 mm silicon. You can also have much larger number of components integrated into the circuit. When you go to more complicated levels, then what you call is an MSI chip you get. MSI means medium scale integration, where the number of components can be anywhere between 10 to 100, and therefore you can see the area of the silicon chip also increases. You have now not 1 millimeter but 4 millimeter by 4 millimeter square, and you get about 0.5 millimeter thickness. So on this one can integrate several tens of components together, then it becomes a integrated circuit, which is a medium scale integration. Then what is more popular these days is the LSI or the VLSI, where you have components which are anywhere from 100 to several millions. So all these million components or thousands of components, hundreds of components can all be formed on the same side of the silicon chip, where the dimensions will be typically 10 millimeter by 10 millimeter square with a thickness of about 0.5 millimeter. So all these technologies were possible because of the developments in the actual semiconductor field. So the whole difficulty is in terms of forming very fine connections between the various components. You can provide isolation between one device and the other device, and these are the very big issues which have to be overcome before we can increase the level of integration. Now it is very commonplace to have millions of components on one single, several memory devices that in this case people talk about. You find they are all made with the VLSI design. Several new designs have come which are coming under the group of very large scale integration. VLSI means very large scale integration, and LSI means large scale integration. Anything above 100 is called LSI, anything very large like thousands and millions, we call it a very large scale integration. And the whole technology by itself is a subject of study. One can take a very systematic study of the design of VLSI chips and things like that at a future stage. But before we go into the actual thing, it is briefly let us look at how it is all done, just to give demystify how the various components can be done on the same side of a silicon wafer. I have just given a typical example here. You see a circuit on top which has got a capacitor at the input, coupling capacitor, you have a diode, you have a transistor, you have a resistor. These are the different components, but you want to get all these components on the same side of the silicon wafer. The silicon strip is called a wafer, silicon wafer, the thin wafer. So it is done by different stages of manufacturing. So I have given here a very simple typical example where you can see this portion, whatever you see, is corresponding to a capacitor, and the second portion is the diode, and the third portion is actually the transistor, and the last one is a resistor. All of them are positioned side by side, and on top you try to put the metal interconnections in the way you want to have the connection in the circuit. For example, the diode cathode will be connected to the base by properly connecting them together, things like that. So this is actually the collector being connected to the resistor, and this is on the base that is being connected to the diode, etc. You can see the interconnections are also made by using gold or any other metal, and you form small tracks of metal to interconnect the various devices, and the whole thing becomes now a circuit. Starting with a P substrate, you try to generate the different layers like the P or the N whenever you want to do diode or a transistor, and you can form the whole device on the scale. This is a very ingenious way of building circuits on the same thing, and you know there are two great men who are associated with this idea. They are John Kilby and Robert Noyce. John Kilby, as you might perhaps know, got his Nobel Prize in physics in the year 2000 for his invention of this integrated circuit technology. Noyce also, Robert Noyce also is associated with this, but unfortunately he died before the Nobel Committee found fit for awarding Nobel Prize to this invention, and therefore he could not be given. But John Kilby, Robert Noyce, both of them are associated with this integrated circuit technology. To go a little further deeper into that, how do we get the different N type, P type, etc. I just want to briefly indicate to you that you have a basic silicon wafer on which you form a photoresist, which is actually a chemical polymer which is sensitive to light, ultraviolet light, for example. So you form a very thin layer by what is known as a spin coating over about 5000 to 1000 angstroms, very small thin area. 1 angstrom is 10 to the power of minus 8 centimeter or 10 to the power of minus 10 meter, and so this you have on the silicon wafer a small layer of silicon dioxide oxide layer, which is called an insulating layer, and over which you put a photoresist film, and then you put a mask on top where you want no device, and where you want the device you don't put any mask, and you expose it to an ultraviolet radiation. Then wherever the light comes, you would find that, for example, in this region there is no mask, and therefore you get the ultraviolet rays reaching here, and they react with the photoresist film, and when you develop it like a photographic film, you would find these things will go away and they will expose the rest of the region below it. Whereas in this place you have put a photo mask, and therefore it will cover the region. So then you can actually etch. When you put an etchant here, you would find the etching will happen only in the place where there is the mask, and in all other places there won't be any etching. So thereby you can form different patterns, very sharp fine details on the silicon chip, and therefore you can have different types of devices developed over this. Let me not go too much deep into that, but I just want to show you another picture here where we have shown actually a transistor. You have a basic p straight substrate into which you generate n type epitaxial layer, and then you have a collector and you have a emitter, and the whatever is in between the n type epitaxial layer forms the base, and so you have PNP transistor on the same surface. On the same surface you have the PNP transistor. So one is the emitter, the other is the base, and the other is a collector. So you can form them, and you can take leads from here, metal leads from these, and then they can be connected to other parts of the circuit. So this forms a integrated transistor. There is another advantage in the integrated circuit design, and that is from the same transistor you can have multiple emitter. This is an example of a Schottky transistor, where you find this is one emitter region where that is shown as P, and you have taken 3 n type region, and you can take 3 emitters. These 3 are emitters, this is the base and this is the collector. So collector, base and emitter. If for the emitter you can choose a very small region and form a n type region here, and in the same again one more. So you can have multiple emitters formed on the same P region, and thereby you will get multiple emitters. That is what is shown here. So this is one great advantage, especially when you go to logic circuits and things like that, you require multiple inputs. ICs, they will look very similar to transistors. For example, I have shown here different types of encapsulation, how the IC is mounted. For application you have to take the small silicon chip, mount it onto a package, and then take the leads to the pins of the package, so that externally you can put them in a given circuit and form the different application circuit that you want. Otherwise it is very difficult for us to use in the lab. So here you have got 2 different packages I have explained to you here. The one is the metal can package, which is basically like your SL100, with which I showed some demonstrations earlier, the TO5 transistor outline 5 style of package with 8 leads for the case of an operational amplifier, for example. So it is an 8-pin metal can with a tab. There will be a small projection in the metal can, which gives us the idea of where from it starts as some reference point. I have shown the bottom view of the same metal can here. You can see this is the tab, and you have got various pins here. All the pins are designated with reference to, for example, this is a voltage, this is an output point, this is an offset null, V minus, non-inverting, inverting, etc. And this is a symbol for op amp. You have already seen also when we discussed about difference amplifier. So this is one metal can. The other one is a mini dip, DIP. DIP means dual in line package. So you have one line of outputs here and one more line of outputs on the opposite side parallel to each other. This we call dual in line plastic package. There is a plastic cover put on the silicon chip, and the various contact points are taken from the silicon chip to the small pins over here, 4 plus 4, 8 pins as the case may be, and you can form different circuits with encapsulated in plastic mini dip. So you can see here the corresponding pin diagram. These are all usually from the top view. So you have 1, 2, 3, 4 from the top. You have to look at this, and to identify that usually you will have a inundation here. That is what is shown here, small cavity here. That cavity will come at the top here, and that shows that to the left of that is 1, 2, 3 when you look from the top side. This is mini dip. To just give you an idea, I have brought here 2 devices. I hope whether you can see it now. You would be able to see I have brought 2 such operational amplifiers, one on a metal can, another on a plastic dual inline package. You can see here on the screen, this is a metal can TO5 package. It has got 8 pins, and the other one is actually a mini dip, 4 plus 4, 8 pins are there. This is also an operational amplifier. So this is an operational amplifier, this is also an operational amplifier. Both are integrated circuit 741 operational amplifier, which is one of the very popular operational amplifier. If you look at the sides, you will be able to see the pins here. there are several pins over here. Similarly, the 4 pins on one side you are able to see, right. You have other packaging schemes also available. For example, here is a 14 lead dual inline package. When you come to digital electronics, for example, you will come across several such devices. All of them have 7 on one side and another 7 on the other side. 14 pin dual package, you have 16 pin, you have several other 40 pin and things like that for different types of circuits. You also have a 10 lead flat pack, where you have a flat pack with 4 plus 4, 8 pins on either side, and that also is another package. This is not generally for general purpose use, we use either the metal can or the plastic. One other thing that we should realize when we go to the operational amplifier is that we most of the time require a dual supply. What do you mean by a dual supply? Your duals, I have shown here what is a dual supply. A dual supply, as the name suggests, is actually 2 supplies. You have to have 2 supplies. There is I have, for example, I have used 2 15 volts batteries. Then you interconnect them in series. How do you interconnect them in series? You take the positive of one of the battery, connect to the negative of the other battery, and keep that junction point, which is connecting the 2 batteries, as your common point or the ground point. So if you now look at this end of the battery, one of the batteries, this is grounded, that means the negative is grounded, and therefore it becomes a plus supply, plus with reference to ground. If you look at the other side, you find the plus end of this battery is connected to ground, and therefore what you get is a minus supply with reference to ground. So you have now 3 terminals from 2 batteries. One is the plus terminal, the other is the minus terminal, the third one is the common terminal, which is the 0 terminal. So with reference to the 0, this end is plus 15 volts, this end is minus 15 volts. So we require this. I have shown here a very simple picture where the op amp, the symbol is shown here, is connected to V plus and V minus are now connected to 2 batteries in the way I showed you here, and the center point is maintained as the common ground, and you have plus going here and minus going here. This is what we call a dual supply. You require a dual supply so that you can have large amplitudes of signals amplified by the operational amplifier when you have AC signals. But we normally in our circuits, when we draw different circuits with operational amplifier, we will not show this power supply connection in detail, because this is understood. That is why I spend a lot of time explaining to you how to do this in actual situation by using 2 different batteries, so that in future we need not worry about this, everybody knows, and so we will just show that there is one V plus and one V minus. That obviously means there is also a common ground. So this will be the symbol that we will be using when we describe different circuits using op amp. But if you find in the lab you do not have a dual supply, you do not have 2 different supplies which are having floating terminals not connected to any common or ground. If you do not have such, then it becomes difficult. How do you generate a dual supply? I have given a couple of suggestions here. You can see if I have one single power supply, I can put 2 resistors R and R, reasonably large value resistors, and keep the center to a ground, and then you find with reference to this ground, this end will be half the voltage of Vs by 2, and this end will be half the voltage on the other side minus Vs by 2. So you find I can have additionally some capacitors here, so that takes care of any transients, and therefore you would find when I have such an RC combination parallel connected together and the center connected to ground, I can have plus Vs2 and minus Vs2 corresponding to the Vs that I use, and this can be used in our operational amplifier circuits. The other way to do that is use the same Vs supply and introduce 2 Zener diodes. You have an RS here, we have already seen that no Zener diode which should be connected without the series resistor. So there is an RS which takes care of the current, to limit the current, and you have the 2 Zener diodes, and depending upon the breakdown voltage of the 2 Zeners, you will have 2 voltages corresponding to the breakdown voltage of the Zener, and because this end is connected to ground, this end will become minus, this end will become plus. So you will have plus VZ and plus VZ on either side with reference to minus VZ on the other side with reference to ground. This can also be used as a dual supply for a operational amplifier. So I have shown you that we require a dual supply, and you can get it from 2 different batteries by series connection and keeping the common to the ground, or you can use a single supply and generate the dual output from that by using a couple of resistors or Zener diodes. Okay. You can also, this is another example of obtaining dual supply. I will not spend too much time on that. I will explain to you different types. Now let me move on to show you, not to frighten you, but to indicate to you the importance of the actual circuit inside the operational amplifier. I talked to you about the operational amplifier 741. This is a typical schematic diagram, circuit diagram of the 741 operational amplifier. There are some striking things that I wish you recognize immediately on seeing the picture, and that is, you find you have more transistors. You have really, the transistors are numbered here, Q1, Q2, Q3, Q4, etc. You find the last transistor is Q20. That means you have 20 transistors in this circuit. And if you look at the resistors, you will find there are only up to R11. So you have only about 11 resistors, 20 transistors. You have more transistors than resistors. And do you have any capacitors? Yes, you have only one capacitor at the center, which is actually a compensating capacitor, frequency compensation. So you find you have 20 transistors, about 11 resistors, and one capacitor. So this is in a striking contrast to what you normally come across in discrete electronics. In discrete electronics, you would find you will have very few active devices, you will have more number of passive devices like resistors and capacitors. On the contrary, when you come to the integrated circuit, you find you have more number of active devices and less number of passive devices. This is a very important characteristic. This is due to the basic technology itself, and that is one of the reasons you would perhaps realize that learning integrated circuit operational amplifier can be very exciting, because you can start afresh. The whole technology, the design of circuits, everything has to be completely different from the philosophy that we normally follow when we make discrete circuits with different transistors, etc. So this is what I wanted to show it to you, and later on we will try to understand some of the basic ideas in this. To make things simpler to you, I have shown this in the form of a block diagram. Basically, the operational amplifier will have a differential amplifier at the input, because you cannot have capacitors, large value capacitors in integrated circuit formalism. Then you go for a differential amplifier, which again looks only for the difference in signals, and therefore it will eliminate the common DC signals from coming from one stage to the other. So you have a differential amplifier as the first stage, and you can have some additional stages of gain, and finally you have a class B push pull emitter follower drive circuit for driving the loads across the amplifier. So this is a general block diagram. You can see that simple diagram is the simplification of what you saw previously in the earlier style, which has got 20 transistors, 11 resistors, capacitors, etc. But as far as a given circuit is concerned, when you want to analyze a circuit, it is much simpler to look at an amplifier, be it a normal amplifier or an operational amplifier. You know, every amplifier at the input side will have one simple Rin resistance, input resistance, and at the output side I can isolate and replace it with a voltage source, where the voltage source is given by AOL into V1 minus V2. There are two voltages V1 and V2, because it is a difference amplifier at the input stage. It is the V1 minus V2 which matters, and that is multiplied by a gain factor, AOL, gain open loop, and that becomes a voltage source for the output side, and you have a small resistor in series which is called the output resistance. So this is a very simple diagram or the equivalent circuit of an operational amplifier when you want to analyze the various configurations of the op amp with the external resistors, capacitors, etc. Okay, what are operational amplifiers? Let us start looking at in some detail. Operational, the name itself suggests that they are capable of performing mathematical operations. That is why they are called operational amplifiers. These were the heart of analog computers in those days. We have plenty of analog computers in those days. Now we have most of the computers digital computers. So these analog computers, some of you may not have heard of them. They used to have large number of these operational amplifiers. They would perform different types of mathematical operations like the multiplication by a constant, summing amplifier, difference amplifier, integrating circuit, differentiating circuit, and things like that. Several of the mathematical operations can be performed electrically on electrical voltages, electrical signals, and that becomes very useful. How? We would see now. Basically, they are very high gain amplifier, DC amplifier. They are very high gain DC amplifier. How an analog circuit works? I will briefly give you a simple introduction. Any physical phenomena can be represented by a mathematical model. We all know that. When usually in the form of a differential equation. If I want a heat conduction in a metal, it can be very easily written in the form of a differential equation, where you can introduce some boundary conditions with reference to the source and the boundaries of the metal and things like that, and you can solve and get complete information about the distribution of heat and the temperature and things like that. So you have to have, for every physical phenomena, in principle one can obtain a mathematical model, and that mathematical model, if it is in a differential form, many physicists will be very happy, because differential equations can be very easily solved, and you can impose some of the boundary conditions and try to realize the actual situation with reference to the model that you have looked at. If the differential equation can be solved electronically, it provides you an additional feature. Then what happens? For every electrical parameter, you can associate an actual physical parameter in the real world, and thereby, instead of building different designs in the real world, you can build a simple circuit which involves only inexpensive components like resistors, capacitors, and voltage sources and things like that, and you can form your differential equation out of that and try to solve the differential equation electrically and measure the different voltages, and you would be able to understand, relate those values, magnitudes, to the actual magnitudes of the parameters which they are representing in the electrical analog with reference to the real physical world. For example, I have just discussed here in a simple way that if you want to study the radiation leak from a nuclear power plant, maybe Kalpakam or whatever, through a concrete wall, we are worried about radiation leakage from the reactor. So what is that we have to do? We can always write an equation corresponding to the thing. So we want to know what thickness will be able to optimize the radiation leak from inside. So in a very simple way, the radiation source is inside. You have a concrete block which is a wall, and you have an outside world in which you want to detect what is the radiation leak still persisting after passing through the concrete wall. This can be very easily equated to a voltage source connected to a series resistor, and then you are trying to find out what is a potential drop through the resistor at the end of the resistor in a circuit. So it is a very similar situation. If I increase the magnitude of the resistor, more will be dropped across the resistor and less will be available at the output terminals. Similarly, if I have bigger concrete wall, thicker concrete wall, the radiation coming out at the end will be much smaller in magnitude perhaps. So you can see now the radiation source can be equated to a voltage source, the thickness of the wall can be related to a resistance, and what you get at the output will correspond to the leak that happens. In this case, the measured voltage at the output can be related to the radiation leak at the output. So this is a very simple scheme to show you that an electrical analog can be built to a real world situation. And if the real world situation requires a differential equation, then we must be able to formulate a differential equation and solve it electrically. Then we would have perhaps modeled the actual real situation with an electrical analog. And what is the advantage here? If you want to change the thickness of the thing, all that you have to do is increase the value of the resistor, which is much simpler than building a concrete wall and changing the thickness. And therefore, the cost of trying out modeling or prototyping becomes very simple. You have to have only very inexpensive components like resistors, capacitors, and you would be able to model the actual real world situation with this. So this was the impetus for designing things like operational amplifiers in those days. And it will be interesting to know that in those days the operational amplifiers were designed with vacuum tubes and transistors even. But with the development of the integrated circuit technology, nowadays all the op amps are in the IC form. They are very small in size. There are several advantages. They operate at very low voltages, very low power levels, whereas if I have vacuum tubes and transistors, sometimes for example I have to operate them at very high voltages like 100 200 volts, and in the case of transistors I should apply 20 30 volts. In the case of op amps, you can have even 1 volt 2 volt operational amplifiers which can operate on very low voltages and very low power levels. This, apart from this advantage of miniaturization and power supply and things like that, you also have several additional features when we go to operational amplifiers. One of the important feature I would perhaps briefly mention is the reliability of the performance of the op amps improves because you have made them in integrated circuit form. Why is it so? This is not difficult to understand. The devices are integrated on a silicon. I have shown you 20 transistors, 11 resistors and 1 capacitor, all integrated in a very small region of less than 1 millimeter by 1 millimeter square. And therefore, what is going to happen? What is the advantage of that? If I have 2 transistors formed on a silicon substrate for a differential amplifier configuration, they perhaps may not have identical characteristics if I have designed them using discrete transistors. But if the same circuit, if I design with integrated circuit, then you would find the 2 transistors will be very close to each other, only separated by few micrometers away, and therefore they will perform almost identically, much better than 2 discrete transistors. This is because even if the discrete transistors are obtained from the same batch while manufacturing, you would find they would have been formed at 2 different points in a furnace. When you try to make them, dope them with p type or n type in the semiconductor, you would find they will be separated by few millimeters or centimeters, and therefore the pressure, the temperature, the doping level, the concentration of the gases and things like that are all will be different at the 2 different points which are separated by several millimeters or centimeters in the furnace. But if you look at the same design in an integrated circuit form, you would find in the same furnace these 2 will be few microns away, and therefore the differences in temperature, the doping level, the pressure, etc. will be very small, and therefore both the transistors will almost be forming in an identical manner. Therefore they will have identical characteristics. If they have identical characteristics, as a difference amplifier, their performance will be enormous, improvement in the performance of these transistors when you do them in integrated circuit technology. Right. So an operational amplifier which started with an application for the case of analog computers, when they came in a very tiny form with excellent performance characteristics, people found that it is very useful beyond the levels of integrated analog computers and things like that. So every designer who wants to design quickly some good amplifier for his instrumentation application or medical application or aerospace application or whatever you have, then you would find those people, the first choice will be to buy an integrated circuit operational amplifier and use it for their own applications. And therefore there is an explosion of applications when it comes to making use of op amps for by different people. Okay, having talked so much about operational amplifiers, then we should try to look at some of the characteristics of the typical operational amplifier. I have given here in the table the characteristics of an ideal operational amplifier and also a typical operational amplifier. In this case I have taken LM741 as a typical operational amplifier, which is a very popular, 741 is a popular operational amplifier. So you can see first characteristic is what is called open loop voltage gain. We show it by a symbol AOL, and ideally the open loop gain should be infinite. But in reality for a typical case of a 741 it is 10 to the power of 5 or 100,000. It is an enormous gain. This is actually the gain factor. The relationship between the output voltage to the input voltage is 100,000 for the case of. We saw even to get some 20-100 with transistors we have to get lot of effort, we have to put lot of effort and then analyze it using H parameter, that, these and all that. So it takes enormous effort to design even a gain of 100 or 200 in the case of transistors, but you find here with a integrated circuit form you can very easily get a gain of 100,000 by special circuit design. When you look at the gain, the bandwidth, the unity gain frequency bandwidth, you find the ideal operational amplifier will have infinite bandwidth. That means all frequencies from 0, that is DC, to very high frequencies it will have the same gain without any drop, whereas in the case of a typical example of a 741 it is about 1 megahertz. So as long as you have the gain of 1, you are up to 1 megahertz, the gain will be almost the same. It will not fall from 1, it will perhaps come up to about 0.7 times or 70% of 1, but then it is the bandwidth is 1 megahertz, which is a very large number, 10 to the power 6. Similarly, if you take the input resistance R in, for an ideal say case it is infinity, and for actual typical case it are about 2 megohm, that means 2 million ohms, 2 followed by 6 zeros, very large number. If the input resistance of an amplifier is very high, it is good. We have already seen the characteristics of a basic voltage amplifier is that it should have very high input resistance. Similarly, output resistance of an amplifier, operational amplifier, in a typical case, in an ideal case it should be 0. In an actual case it is about 75 ohms, which is reasonably very low, few ohms only, and therefore you find this is a device 741 typical device which is very close to the ideal situation. 100,000 is almost very large, 1 megahertz is about 1 million times, and 2 megohm is again 2 million, very large, and 75 ohms is very small in terms of magnitude, and therefore you find operational amplifiers are much closer to an ideal situation than your transistors, which are non-ideal devices, and that is the reason why you have to model them by different ways. You can do it in different ways, you can do H parameters, R parameters, Y parameters and things like that, and even then you find you have to incorporate number of approximations to analyze, because otherwise the circuit analysis becomes very complicated, whereas here it is very simple because it is very close to the ideal situation. There are other parameters like input bias current, input offset current, input offset voltage, etc. We will discuss at a later stage in detail about some of these things. If you look at the ideal situation, you find they will either be 0 or infinity depending upon the characteristic, whereas in a typical case these are some magnitudes, 80 nanoamperes for example input bias current, input offset current is about 20 nanoamperes, input offset voltage is around 2 millivolt, common mode rejection ratio is expressed in dB decibel, which we have already seen is around 90 dB, which is 80 dB is 10 to the power of 4, so it is about 10,000 times or more 90 dB. Okay, we will try to look at in some detail now. Ideal op amp as infinite input impedance. Of course this is understandable, as I already mentioned to you, because this will make the entire signal, when I apply a signal from a signal source, the entire signal should be applied across the amplifier. I do not want anything to be lost, but you know all sources will have a source resistance or source impedance. So this voltage will be now applied across not one resistance or one impedance, but two impedances. One is the source impedance, the other is the input impedance of your amplifier. Only when the input impedance of the amplifier is very large compared to the source impedance, you will find the entire signal voltage will be applied across the amplifier terminals. Therefore, it is in principle we do not know anything about the input source, and therefore it is better to design an amplifier which has got very large input resistance, so that it will take care of any kind of source even if it have very large input impedance. Because your input impedance of the amplifier is very large, you would be able to manage and get all the signal applied, most of the signal applied across the input terminals of the amplifier, and thereby you will be able to get the entire voltage. So this is understandable why the input impedance of an ideal amplifier should be infinity, or in the typical case it is about megohms, 2 megohms or something. So that is clear. The output impedance of an ideal amplifier is 0. This is also is understandable because the output of an amplifier is used to drive a load. When you want to drive a load, then your source impedance from the source, your amplifier output now becomes a source, and therefore the source impedance should be very minimum, then only the entire voltage will be across the load, and that way the output of a operational amplifier should be an ideal voltage source with 0 internal resistance, and that is why the output impedance of an amplifier should be minimum. Usually ideally it is 0, in actual case it is about 75 ohms. So this also we are able to understand why we should have, but even the unity gain bandwidth should be infinity, we can understand. We want amplifiers which will amplify all signals irrespective of the frequency, whether it is low frequency, high frequency, it should amplify by the same extent, by the same magnitude of the gain. It is always very difficult to realize such amplifiers, we all know that every amplifier will have a finite bandwidth. So in principle ideally we should have infinite bandwidth, understood. But why should the gain of an operational amplifier, ideal operational amplifier, be infinity? Why should it be infinity? Or why should a typical operational amplifier should be very large, 100,000, why not less? There is also a term I used for the gain, I did not call it as a gain, I mentioned it as a open loop gain. What is the meaning of the open loop? Why we should have a very large gain magnitude? And you can imagine that these two statements, these two questions have got some link in between them. So when I explain to them, perhaps you will be able to appreciate this. We can understand this by looking at the concept of feedback in amplifiers. Feedback, as a matter of fact, is a very important concept in all electronics and in control. If you want to close a pen, for example, you take the example of a pen and to try to close the lid of the pen by closing your eyes. I can assure you, if you keep trying, you would find it is very difficult to close the pen exactly to the nib. That is, you just take the pen, you open up the lid, close your eyes and try to match them. You would find you will always miss. You will not be able to do that unless you see them with your eyes, and then you will move automatically, your hands will get the message because your eyes are seeing your movement of the hands. They will inform the brain how your hand is moving, whether it is moving in alignment or not, and then the hand will be automatically given the command by the brain to move and close it correctly. Here is a case of biofeedback. The pen and the hands are coordinated through the signal obtained through the eye to the brain, and so the brain is able to control using the feedback that it obtains from the eye, through the biofeedback. And therefore feedback is a very essential, important, innovative concept in all electronics, and that is one of the very important thing that perhaps we should now look at. Feedback is employed in an amplifier also. What do you mean by feedback? You have to take a small fraction of the output voltage and apply it at the input along with the signal. When you take an amplifier, give an input, you get an output. So take the fraction of the output and then give it along with the input, then you have given a feedback, you are feeding it back into the input. This feedback can be of two different types. One corresponds to negative feedback when the output is not in phase, as actually it is out of phase with the input, and you have another feedback which is called positive feedback where the output voltage is in phase with the input voltage. So you have two different types of feedback, negative feedback and positive feedback. Positive feedback in an amplifier will in general lead to oscillations. So when we discuss about oscillators, we will perhaps go much deeper into positive feedback and show you the consequences of what positive feedback, how positive feedback can be exploited to design different types of oscillators, etc. But right now we would concentrate more on negative feedback. So what do you mean by negative feedback? Once more, I take the fraction of the output and connect it at the input out of phase with the input signal, 180 degrees out of phase. So if the input is increasing, the output will be decreasing, the feedback voltage will be also decreasing, then it becomes a negative feedback. You can immediately realize when I do that, some of the input voltage will be cancelled by the feedback, and therefore the actual input voltage which is applied to the amplifier will be decreasing, and therefore the gain will also decrease. You can intuitively guess that when you give negative feedback, the gain will decrease, and it is indeed true that when you give negative feedback in an amplifier, the gain will decrease. So though you feel that this will be disadvantage to the amplifier, because you do not want the gain to decrease, you want the gain to be more, but you can see this is a great advantage in several other parameters of an amplifier, like input impedance, output impedance, bandwidth, distortion. All these characteristics will enormously improve depending upon the degree of feedback that you give, amount of feedback that you give. The more the feedback that you give, more will be an improvement in input impedance, output impedance, bandwidth, distortion, all those things. So therefore people are very much interested in introducing feedback, that to negative feedback in amplifiers, to improve the characteristics of the amplifier. That is one of the reasons why we want to have very large gain for our amplifier. I will explain to you in a minute now. I have here on the screen, you can see an amplifier with a gain A without any feedback. You have an input terminal, you have the output terminal. Then what we do is take the output terminal in parallel and connect to a network here. B is another box with a network there, which is a fraction, beta is a fraction. So a fraction of the output voltage will be taken, which is called Vf, the feedback voltage, and that is given in opposition to the input voltage. This is plus minus and this is minus plus. So when it is given in opposition, what will be the balance that is applied across the terminal? I call it V epsilon, and that is what is actually applied now. So what is Vf? Vf is actually beta times V output. It is beta is less than 1, it is a fraction, and therefore a fraction of the output is given as the feedback voltage Vf, and the V epsilon, which is a voltage actually connected across the amplifier, our amplifier, is what I connect outside, V in minus whatever I have given as a feedback Vf, because they are in opposition, 180 degrees out of phase. But Vf is beta V naught, therefore I substitute here V in minus beta V naught, and we also know from this amplifier characteristic V output is A times V epsilon, which is the actual input connected at the terminal. So V output is A times V epsilon, and V epsilon is V in minus beta V naught. When you rearrange them, you would find V naught by V in, which is the gain of the total amplifier including feedback. I call it AF, A with a suffix F. This is the amplifier gain with feedback, and that is equal to A by 1 plus A beta. This is what I get, an expression for the gain of the amplifier with feedback, with negative feedback. If it is a positive feedback, this plus sign will be minus, where AF is the gain with feedback, A is the gain without feedback, which we call open loop, because there is no feedback loop. This is a feedback loop. This loop is, when it is missing, then we call it as an open loop. and beta is a feedback ratio. I already told you beta is always less than 1. So now what will happen in the limit a tending to infinity? When a tends to infinity, a by 1 plus a beta will almost be equal to 1 by beta. So you divide numerator and divided by a, you would find this is very easy to see that the gain with feedback when a tending to infinity will be 1 by beta, and that means it is independent of a, the gain of the amplifier. It depends only on beta, which is a feedback ratio, which is actually in our hands. The beta is done by us outside the amplifier by using some small resistor network, and therefore the amplifier becomes independent of its own characteristics, and it can be very easily controlled by having a couple of resistors outside by controlling the feedback, and therefore operational amplifier becomes an excellent device for different applications. So that is the reason we must have very high gain, a tending to infinity only. This will be true. The larger the value of a, the better will be with reference to 1 by beta, and therefore in general operational amplifier, ideal operational amplifier should have infinite gain. An actual amplifier, for example 741, has a open loop gain of 100,000. Having said that, now I must also perhaps discuss in the next lecture what are the different types of feedback that we can give. I have only talked about general principles of feedback. We can also imagine that we can have different types of feedback. I can sense voltage or current from the output side, and then give as a voltage or current at the input side. So this variation in the way, the type of feedback that I incorporate in a given amplifier, you would find the amplifier characteristics can be completely modified. It will no more be a voltage amplifier, it may become a current amplifier, or it may become a current to voltage converter, or it may become a voltage to current converter. So by just manipulating the external resistors for a given operational amplifier, I will be able to design different types of circuits which are very close to ideal, and therefore which are performing wonderfully well. All these are possible by the simple device that I have, which is called operational amplifier, which in principle from the market you will get it for about 5 to 10 rupees or so, not very expensive, and with that you can try to build different type of exotic circuits for different types of applications. So we will discuss in the next class, for example, about the different types of feedback that we can give, and we will try to incorporate the different feedbacks and try to see what results from that type of a feedback, what type of a circuit, what type of characteristics we achieve by giving such feedback. We will discuss next time. Thank you.